Okay, so far we have looked at the result of the weak low large numbers and central limit theorem, and also we discussed the meaning of those two important theoretical findings in probability theory. From now on, we are going to prove the weak low large numbers and central limit theorem. The proofs of those two theorems require some useful knowledge about the inequality and also something called the moment generating functions. And those are the very important tools that are used frequently in probability. So it's very nice to learn those tools, which we can apply to other areas. Okay, so we're going to first talk about the proof of the weak low large numbers. In order to prove that, we need to know the two important inequalities. So first, that is the Markov inequality. Okay, what the Markov inequality addresses is the following question. So the question is that suppose that we just know the expectation of some random variable. Okay, now can we say anything about the distributions of x? And obviously we cannot exactly the distribution of x because we don't know. But if we know the expectation, somehow we have a very rough estimate about the distribution. So the intuition is that as the expectation gets smaller, then we're going to have a smaller probability of x, which is larger than some constant a, which is essentially the CCDF. Okay? Because this probability corresponds to the amount of the probability mass that is larger than a. Okay? So Markov inequality is that for a positive random variable and for positive constant a, the probability that x is greater than a, and that is bounded by the expectation divided by a. Since this is a bound, this is not equal, so we cannot say exactly that this is equal to this one, but as the expectation gets larger, then this probability gets larger. So these two quantities may have a similar tendencies about the value. Now let's prove that. So for any constant a, which is positive, we are going to define the random variable ya as if the x is between the 0 and a, and then ya is defined as 0. Whereas if the x is greater than or equal to a, then the ya becomes a. Now, since the x is always non-negative, we can say that the random variable ya is less than or equal to x, right? From the definition of the random variable y. Why is that? Because in the range of 0 and a, y is 0, so it's always the x is greater than or equal to ya. And also the x is greater than or equal to a, then ya is a, so then also in this range, we can say that the y is less than or equal to xa. So we can say this thing. And that means that the expectation of ya is less than or equal to the expectation of x. Because of this, okay? All right. Now, what is the expectation of ya? That is, the value that the ya can take is a for this case and 0 for this case. Since the value of the ya is 0 for this case, we can just ignore. Again, we can only consider this, and the value is a, so a, and that is multiplied by the probability that ya becomes a. Okay? Now, ya becomes a, that is equal to the probability that x is greater than or equal to a from the definition of the ya. Alright? Now we are done because the expectation of ya is equal to the a multiplied by the x is greater than a. And we know that this expectation of ya is smaller than or equal to the expectation of x from this. Okay? So we get this. So the Markov inequality says that the probability that x is greater than or equal to some constant, and that is less than the expectation of x divided by a. That's Markov inequality. Okay, let's look at another inequality which will use the Markov inequality in the proof. That is the Chebyshev inequality. So Chebyshev inequality addresses this question. Suppose that we know both expectation and the variance. So in the Markov inequality, let's assume that we just know the expectation, then how can we say about the distribution of x? But here in the Chebyshev inequality, suppose that we know both the expectation as well as the variance. Can we say something about the distribution of x? Now, compared to the Markov inequality case, we know more information, so we may be able to draw more concrete conclusion or the estimation about the distribution of x. That's what we can expect. And some intuition behind this question is that, and for small variance means that more points are concentrated in around the mean, then x is unlikely to be too far away from its mean, right? It's pretty intuitive. Okay, so we're gonna melt down this intuition in the equation. Let's denote that the expectation of x is mu and the variance of x is sigma square. Chebyshev inequality says that the probability that x minus mu, absolute value, is larger than some positive constancy. So this probability is equal to the probability that the x is larger than mu plus c, or x is less than mu minus c. Okay. For example, here's mu. This is mu plus c. This is mu minus c. This probability. Okay. And that is bounded by the variance divided by the c square. And that's will hold for all positive c. Okay. Again, when you look at this Chebyshev inequality, how this probability and the variance are related? Well, if the variance become large, then the x will have more diverse values. So this kind of outside probability will become large. Okay, so as variance large, then this probability will large. And those kind of tendency are reflected in this Chebyshev inequality. Okay. All right. So let's prove that. So first, this probability, the probability that the absolute value x minus mu is larger than c. And since the c is positive and this absolute value is also non-negative, and that is equal to the x minus mu square is greater than the c square, because both are the positive. And using the Markov inequality, okay, so what is the Markov inequality? If x is larger than a is less than or equal to the expectation of x divided by a for both positive random variable x and the positive a. Okay, so if you regard this as another random variable y, and this is some another constant c square, okay, let's say a, this is a, then this is less than or equal to the denominator a and the expectation of the random variable y, which is in this case x minus mu square. Okay, now we know that this is the definition of the variance of x, right? So sigma square divide by the c square. So we're done. So one may ask the question about the, okay, I roughly see the different equations between the Markov inequality and the Chebyshev inequality. It may be very helpful for us to look at the example where each of these two inequality will provide us different bound for the same situation, for the same setting. Okay, so let's look at that. So x is an exponential random variable with the parameter 1. And we know that the exponential random variable, the expectation is 1 over lambda, and the variance is 1 over lambda square. We already kind of memorized that. So that's 1 and that's 1. Okay. Now, also we know that the CCDF of exponential random variable, we have seen this multiple times in the previous lectures, and that is equal to the e to the minus lambda a, where here in this case lambda is 1. So e to the minus a. Okay, this is an exact CCDF. Now let's make comparison the CCDF bounds that we have computed using the Markov inequality and the Chebyshev inequality, and let's compare those things with the exact CCDF. Okay, so in the Markov inequality, we use this probability that x is larger than a is less than or equal to the expectation of x divided by a. So that is bounded by the 1 over a. And what is this? This is a rough estimate about the CCDF using the Markov inequality. We don't know the distribution of x. We just know the expectation. So I make a conjecture about this CCDF, and it turns out that Markov inequality gives us the 1 over a. Whereas in the Chebyshev inequality, the probability that x is larger than a, and since we have to use the variance, so we just put subtract -1 in both sides. Okay, and that is upper bounded by the probability that the absolute value x minus 1 is larger than a minus 1, because the a minus 1 can be negative, so that probability can be large. So it's upper bounded by this probability. So in this case, now we can apply the Chebyshev inequality, and that is the a minus 1 square 1 over a minus 1 square, and this is the variance of x, okay, and this is mu. Okay, so that's 1 over a minus 1 square. Okay, so we get 1 over a, and we have 1 over a minus 1 square. Then obviously for reasonably large a, the Chebyshev inequality will provide a much better bound, because here in this case it's more exact, right? It decays as a quadratic function of a. Okay, but here in this case only it's 1 over a. And this is a very rough estimate, because Markov inequality just uses the expectation, so that's a very small amount of information. Whereas in the Chebyshev inequality, we also use the variance information, from which we can figure out the estimation of this CCDF in a more exact manner. And that's also intuitive. Remember, this both bound means that the bound which is given by the Markov inequality and the Chebyshev inequality, these are the ones that bound the probability of rare events. So what do you mean by the rare event? Because we are computing this CCDF. CCDF is that if a is reasonably large, its probability that x deviates from the expectation. I mean, obviously, any random variable will have more mass, or the concentration around mean, right? And the probability that the x is larger than some constant, where the difference between that constant and expectation becomes larger, we are interested in computing more rare events that does not occur very often. All right, so using these two inequality, we can come up with the value of the probability of rare events. Okay, all right, so let's go back to the weak lobe large numbers. What is the weak lobe large numbers? The sample mean, which is this, converges to the expectation of each guy, each xi, which is the mu in probability. To remember how to prove the convergence in probability, yes, we prove the convergence in probability using, for any given epsilon, we compute this probability, and we need to prove that this probability goes to 0 for any epsilon, right? So in order to do that, we're going to use the Chebyshev inequality. So using the Chebyshev inequality, this probability, the denominator is epsilon square. So again, what is the Chebyshev inequality? X minus mu is greater than c is bounded by the variance of x divided by the c square. That was the Chebyshev inequality, right? So this is an epsilon square, and what this should be the variance of this part, and that is a variance of this sample mean. And what is the value of the sample mean? That is the sigma squared divided by n. Because the variance of the sample mean is 1 over n squared, that's the multiplicatory term, gets out of the variance, then we do the square. And since xi's are independent, the linearity of the variance holds, so n multiplied by the variance of any xi. So this cancels, and this is sigma squared, so this is equal to the sigma squared divided by n. Okay, so this sigma squared divided by n is the variance. Sigma squared divided by n, epsilon squared is the right hand side of the Chebyshev inequality, and obviously for any given epsilon which is positive, as n goes to infinity, this goes to 0, so we're done. This is how we prove the convergence and probability.